Hi everyone, today we're going to talk about using algebra to evaluate limits of functions at infinity. Get ready to unlock the power of math together. Let's dive right in. Okay, so in previous units we've talked about the limits of polynomial functions at infinity. So we've pretty much looked at the end behaviors of those polynomials. So comparing the odd degrees and the even degrees, and then positive or negative lead coefficients. So what we're going to do is we're going to use those kind of same ideas and think about these polynomial functions and finding the limit as x approaches either negative infinity, looking at the left side of our graph, or as x approaches positive infinity, looking at the right-hand side of our graph. So if we look at question number 1, what you're going to notice is that you have an odd degree as well as a negative lead coefficient. So what would happen is my graph would look something like this. So with odd degrees, we'll point in opposite directions. And then if I look towards x approaching negative infinity, I'm looking at the left-hand side of my graph. So what is it doing? It points up towards positive infinity. In question number 2, you have an even degree with a positive lead coefficient. So what that would be like is pointing in the same directions and both pointing up. As I'm looking as x approaches positive infinity on the right-hand side of my graph, my function is approaching the value of positive infinity. In question number 3, you have an even degree as well as a negative lead coefficient. So what's happening? Both of our ends are pointing down. As x approaches negative infinity, the left-hand side of my graph, my function is approaching or pointing towards negative infinity. In number 4, we have an odd degree, right? That is the 3 with the highest exponent. You have a positive lead coefficient, so your graph ends would look something like that. And as x approaches positive infinity on the right-hand side of my graph, my function is approaching positive infinity. Now, when we looked at rational functions at infinity, again, we were looking at the horizontal asymptote. So you're looking at top heavy, bottom heavy, or even Stevens. And we also looked at the possibilities of having slant asymptotes. Now, in calculus, you're going to need to show your work, and what that work looks like would be to do these steps right here. You're going to divide every term by the highest power of x in the denominator. So what that does is that helps us to see what goes towards a 0 and what doesn't as x approaches, let's say, positive infinity. And we're going to simplify our fractions, and then we're going to use the following rule with reciprocal functions at infinity. And those reciprocal functions are pretty much looking at the functions with x in the denominator. So that means that that limit is going to be 0. Now your answer could be a number, which we would know as our horizontal asymptote, or the graph can approach positive or negative infinity, which we know is a slant asymptote. So looking at this question, you can see that this rational function is actually bottom heavy. Okay, which means if you have a rational function that has bottom heavy, then that means that the horizontal asymptote would actually be at 0. So as we evaluate our limit here, as x approaches negative infinity, what we're going to hopefully see as we do our limit is that our answer is going to be approaching 0, which would match up to what we used to know and how we used to prove it. So let's go ahead and do our limit as x approaches negative infinity. We're going to divide every term by the highest degree in the denominator, that is the 2, the x squared. So we're going to take x over x squared plus 3 over x squared, and then divide that by every term gets divided by this x squared. and then 1 over x squared. So as you simplify your limit here, negative infinity, so this will become 1 over x, and then this one will become 3 over x squared, and then divided by 2 minus 1 over x plus 1 over x squared. So then we're going to go ahead and simplify. So with our reciprocal rule, what we know is that these limits are all 0 here. So this is 0, this is 0. So the limit as x approaches negative infinity, as we simplify this, 0 in the numerator, and then just what's left is 2 in the denominator. So what that's going to be is 0 over 2, which we know is 0, which does match up to the way that we used to prove what our horizontal asymptotes were with now our limit work. Okay, in number 6, again, let's just look to see what should we get at the end. This is even Stevens, which means we should technically have our lead coefficients, which would be 2 over 1, which is 2. So our answer hopefully will turn out to be 2, as long as we do this correctly. So largest degree of the x is x squared, so our limit as x approaches infinity. So let's say you have 2x squared over x squared plus x over x squared plus 3 over x squared divided by x squared over x squared minus 9 over x squared. So let's go ahead and simplify. We got 2 plus 1 over x plus 3 over x squared. We got 1 over 9 over x squared. So what we're going to do is use our reciprocal rule. This is 0, and that is 0. So our limit as x approaches infinity, we get 2, and then you get 1. So you're going to get 2 over 1, which simplifies to 2, which matches up to what we know. Okay, in question number 7, we've got, let's see, we have something that is top heavy. Okay, we will have a slant asymptote. So degree on the top is exactly 1 larger. So normally we know if it's top heavy, it would be none, but we do have a slant asymptote here. So let's see, largest degree is x squared. So we have, let's see, x cubed over x squared minus x squared over x squared plus 7 over x squared. And then you have x squared over x squared plus x over x squared. All right, so let's simplify. So what we're going to get is an x, a 1, and then 7 over x squared, and then you get a 1 over x. So we know that this will be 0, this will be 0. So what you would see is you have x minus 1 over x, right? That is our slant asymptote right there. So as we substitute our negative infinities, we have negative infinity minus 1 over 1. But if you're just subtracting here, you're going to have negative infinity, which does match up because if you have a slant asymptote as y equals x minus 1, it does look like this. So as we're looking, as x approaches negative infinity, we're looking at the left-hand side of my graph, which again approaches or points down towards the negative infinities. Thanks for learning with me today, unlocking the power of math one problem at a time. Don't forget to like and subscribe for future notifications on pre-calc videos. See you in the next lesson.